Hey guys, welcome to lecture series on M3 subject. For similar videos, check in my playlist. So in my today's video, I'm going to explain to you all some of the example based on the Cauchy homogeneous differential equation. Already I have explained in my channel entire process and some example based on this method. Okay, these are the very much important questions in perspective of your SPPU upcoming question paper. Okay, so in our today's lecture, I'm going to explain to you all one of the example. That one it is here. Okay, using Cauchy homogeneous differential equation. This one is our Cauchy homogeneous differential equation. So we are going to reduce this differential equation into the linear differential equation with a constant coefficient. Okay, so we are going to reduce this one with the linear differential equation with a constant coefficient by using some substitution. Okay, so we apply some of the substitution method for solving this one. Okay, so without further ado, let's get dive into our today's solution. I will explain to you all how can we go for the substitution here. Okay, yes, so as we know that whenever we have x into dy by dx, okay, whenever we have x into dy by dx, okay, so we write this term as a capital dy, okay, dy. So we are trying to convert this homogeneous Cauchy homogeneous differential equation into the auxiliary equation. Okay, first of all we convert into the linear differential equation with the constant coefficient, then we take it to the linear, then we take into the auxiliary equation, and then we find the complementary function and particular integral. Okay, that is the entire process. So x into dy by dx, we write capital dy. So whenever we have x square, okay, whenever we have x square, d square y by dx square, okay, this is the entire method I already explained. X square d square y by dx square, we write this one as d into d minus 1 of y. Okay, we write this one as a d into d minus 1 of y. So as we have highest power as a x square, so we don't have to go for the cube. So if it is the power third, it is there now, then we write x cube d cube y by dx cube is a d into d minus 1 into d minus 2 of y. Okay, so this is the way to add the differential capital D over here. Okay, yes. So as we have all the values over here, we need to replace here. Okay, just only not replacing these values, we are replacing x also. We are replacing x by some of the values. Okay, so as we know the standard form, we replace x which is equal to e to the power z. Okay, yes. So apply log to the both side. So log x can be written as log of e to the power z. Okay, log of e to the power z. So log x can be written as z. Okay, log e, they are the inverse quantity. Okay, so we write z as a log x. So dz by dx can be written as 1 upon x. Okay, dz by dx can be written as 1 upon x. Okay, these are the all values that we needed here for the substitution in our Cauchy homogeneous differential equation in order to convert into the linear differential equation into the constant coefficient. Okay, now substitute all these values over here. Okay, x square d square y by dx square. Okay, so x square d square y by dx, we write d into d minus 1. Okay, d into d minus 1. So I'm taking y directly out of the bracket. Okay, so that's why I'm not going to write y over here. Minus 3 times x dy by dx. X dy by dx is a dy. Okay, then x dy by dx. Okay, x dy by dx is a dy. So 3 multiply here 3x dy by dx, which is equal to 3 times dy. Okay, replace here 3 times dy. So y I'm taking out here. Okay, plus 5. Again y out here. Okay, so y it is out there. So x square. Okay, x which is equal to e to the power z. Then we write x square as a, now see that if you confuse here now, if x which is equal to e to the power z. Okay, x is e to the power z as we are taking substitution. So I want the x square. So x square means take both of the side square, e raised to power z square. Okay, then we multiply their power, e raised to power 2z. Okay, so x square can be written as e raised to power 2z. Put here e raised to 2z. Okay, x square written as e raised to 2z. Again sign of log of, what is the value for x? We are taking x as e to the power z. Okay, e to the power z. Okay, so see that log and e also coming together, so it can be cancelled here. We write the sign of a z directly. Okay, yes. So as a exponent, as a rule of exponent, we write z into the power multiplicand over here. Okay, let me solve next step here. So what we write, d into d square minus d into 1 minus d minus 3d plus 5. Okay, okay, minus 3d plus 5 which is equal to y into y which is equal to e raised to 2z into sine of, okay. So I want the value for this term log of e raised to z. Now see that how I'm going to solve it here, okay. Log of e raised to z. Apply exponent rule for logarithm, that z it is going to be the multiplicand here, okay. Z which is equal to log of e. Then if with z into log of e, so it gives us the value 1, so it remain only z, okay. So we left here with the value of z only, okay. Yes, so d square minus d minus 3d plus 5 which is into y which is equal to e raised to 2z into sine z, okay. This is our given phi of x and this is our required f of d, okay. So we'll take this one for further and we go for finding the solution here, okay. So we got the d square minus d minus 3d minus 4d plus 5 which is equal to 0. This one is a simple quadratic equation in the form of a d, so it is way easier to find out the root, okay. Yes, so the roots are coming here. So if you don't know, then you can directly apply the formula. So minus b means minus b plus minus square root of b square minus 4ac upon twice of a, okay. This one is the way that we find the roots, okay. So bac, where it is coming, the value for a which is a coefficient of d square 1, value for b which is a minus 4, coefficient of d, and value for c which is a 5, okay. So we have all a b c over here, put all this value here, b a c everywhere, okay, and you will get the required root, okay. So after solving these roots, I already solved this one, so I'm going to write the root, okay. This one is way easier to find out the root, okay. So if you are confused to finding this, let me know in my comment section. I will come up with a similar video, okay, for finding the roots of a quadratic, cubic, or all the equations, okay. Already I explained this one in my previous lecture. See these videos for your reference. So the value for a is a 2, b is a 1, okay. So using this one we are going to write the solution, okay. As we have complex root, that means a plus minus bi which is equal to 2 plus minus I. The value for a which is a 2 and value for b which is a 1, okay. Compare all these values, you will get the a and the b, okay. So complementary function we write in the form of a z, as we have function in the form of a z, that's why we are writing complementary function in the form of a z, not the form of a x. So don't get confused in the in comparison of x and z, okay, as we are completely eliminating that x from here. So if you are eliminating that x from here, then you don't have to take x again here in downside, okay. So we have to work with the value of a z only. So complementary function e raised to ax, that means value for a is a 2, e raised to 2z, okay, e raised to 2z, c1 cos bz, okay, c1 cos bz plus c2 sin bz, okay, c1 cos bz plus c2 sin bz. This value you must have to replace over here, okay. Yes, so let's go for next step. We are going to replace that z also here, okay. So replace z to the replace that z, okay. So we are going to replace that z with the its regular values, okay. Z what we have here, so x which is equal to e to the power z, then we write a z as a log x, okay. We are going to replace z as a log x here, so you will get the complete complementary function in the form of a z only. So in my previous example now, I didn't substitute this value back, so you have to check that one from here, how we can substitute, okay. So I directly found the value, with the form of a z. We do not want z, we want the solution in the term of x and y, okay. So you have to revert the values, okay. So how I'm going to write it here now, see that complementary function, it can be written as e raised to 2 times z. What is the value for z, which is a log x, okay. Put that log x here, e raised to 2 times log of x, okay. Yes, again under bracket c1 cos z plus c2 sin z, c1 cos log of x, we are replacing z as a log x, okay. We are taking that revert back, plus c2 sin, okay, c2 sin the log of x, okay. So I replace the b as 1 here, okay, the value of b as we have 1. Replace these values here. This is just a simple substitution, okay, don't have anything complicated. Yes, okay, this one is our required complementary function. So if you want, you can go for further solving, okay. E raised to 2 into e raised to log of x, so we write e square into x, okay. Yes, so you can go with that way, or you can keep as it is, okay. This one is a required complementary function. So for finding the particular integral, we know that we write 1 upon f of d into phi of, okay, we will write 1 upon f of d into phi of x, okay, as we have function in the form of z, so we write 1 upon f of d into phi of z, okay, as our particular integral, okay. Yes, so put 1 upon f of d. What is the value for f of d? As we have here d square minus 4d plus 3, okay, 1 upon d square minus 4d plus 3 as our given f of d into phi of z. What is the value for phi of z? We are x square sin z, okay, so we are taking this one as a z, okay, phi of z e raised to 2z sin z, okay, we are writing this one as e raised to 2z into sin z. So those who have attended my previous video lectures now, you can solve it very easily later on, okay. We have challenging part, this one only, to convert our homogeneous differential equation, okay, Cauchy homogeneous differential equation into the our linear differential equation with the constant coefficient, okay. This one is the part quite confusing to get this one, okay. I hope you all have understood how this part is coming, okay. Okay, so later on we just have to apply simple result, e raised to 2z, take it once, and sin z is like we have e raised to z into v. So okay, we have to apply some standard results here to solve this one. Okay, let's go for solving this particular integral further. So I explained in my previous case that whenever we have e raised to ax into v, e raised to ax into v, such a phi of x present here. In such a case, what we do, we take e raised to ax out here, okay, e raised to ax, we take it out here. 1 upon d, instead of a d we write a d plus a, into v sin z we keep as it is, okay. So apply that standard form here. So if you are not aware with this standard form, let me show you all now. See that standard form I am applying here, f of x is equal to e raised to x into v, where v is a function of x. Then we write particular integral 1 upon f of d phi of x as 1 upon f of d e raised to x into v, okay, e raised to x into v function if it is in this form, and v is the function of x here. So e raised to x we are taking out here, instead of a d we are writing d plus a, and we are keeping v as it is, okay. So we are taking that result here to solve this example, okay. Yes, so take e raised to 2z common here, e raised to 2z, okay, under bracket 1 upon now we are what we are going to do, we are going to replace d as a d plus 1, okay, we are going to replace d as a d plus 1. So what is the next step it coming here, what is the next step it is coming, actually d plus 1 not, okay, the value for a, and as we have value a which is equal to 2 here, okay, then we write d as a d plus 2, okay, d as a d plus 2. So d plus 2 bracket square we write here, d plus 2 bracket square minus 4 times d plus 2 plus 3, okay, this way I replace here d plus 2, okay, we write a d as a d plus a, and the value for a which is a e raised to az, that means a which is equal to 2 over here. Then what is the next step it coming here, e raised to 2z it is out here, sin z keep as it is, okay, we are not going to change anything here in a sin z, okay, e raised to 2z keep as it is, okay, 1 upon d plus 2 square, expand this term, multiply this one, go for the calculation, you will get the value d square plus 1, okay, d square plus 1 in this form after calculation of all these terms, okay. I'm not going to calculate here, it is time taking, it is just simple expansion, a plus b square as a square plus twice of ab plus b square minus 4d minus 8, okay, plus 3, then go for the calculation, you will get the value 1 upon d square plus 1, okay, and sin z as it is, okay. Now we know that whenever we have sin ax plus b, we replace d square as a minus of a square, okay. So let's go for the replacing the value here, we are applying standard form, so ax plus b, that means az plus b, a which is equal to 1 over here, so we replace d square as a minus of a square, a which is equal to 1, so d square is equal to minus of 1 square, that means d square which is equal to minus 1, okay, minus of 1, okay, minus we are not taking that square of negative, okay, d square it is a minus 1, so if we put d square as a minus 1, we see that denominator it goes to 0, so in such a case we have to apply next condition. So in our next condition we multiply z to the denominator and we take differentiation of a denominator, okay, numerator multiply z, okay, e raised to 2z keep as it is, multiply z to the numerator z, and differentiate denominator with respect to d which is 2d into sin z, okay. Again replace d square as a minus a square, that means we write a minus 1 here, okay, No, we don't have minus a square. Okay, that means we have to take 1 upon d as a integration. Okay, so e raised to 2z into z, okay, divided by 2, 1 upon d into sine z over here. Okay, yes, 1 upon d into sine z, and we know that 1 upon d into f of x as a integration of f of x. Okay, this one is the standard form, you just need to remember. Okay, yes, we write e raised to 2z into z divided by 2 sine z. Sine z has a differentiation with respect to z is a cos z. Okay, yes. So we want this particular integral in the form of x. We do not want in the form of a z. So replace the z as a log x. Okay. So e raised to 2 times log of x multiply by log of x. Okay, e raised to 2 times log of x multiply by log of x divided by 2 into cos of log of x into cos of log of x. This one is our required particular integral. Okay, yes. So if you want, you can go for further solving, or you can keep this solution as it is. This one your required particular integral. Okay, yes, this one is the entire solution for our given Cauchy's homogeneous differential equation. Okay, so here first we reduce our Cauchy homogeneous differential equation with a linear differential equation with a constant coefficient, and there is the auxiliary equation. First we found here the complementary function in the form of a z. Okay, so we don't have to keep that z as it is. Remember, we are replacing that z in the form of x. As we have given example in the form of x, give the solution in the form of x, not in the form of a z. Okay, so I replace complementary function over here. So similarly go for the particular integral. So go for finding particular integral over here. Replace the values here, you will get the required solution. In the form of x, we want the solution, and we want the complete solution. Complete solution means complementary function. This complementary function plus this particular integral, this one is your required complete or general solution. Okay, so I hope you all have understood my today's lecture, guys. Even after, if you found anything difficult, confusing, let me know in my comment section. I will come up with the similar videos. Okay, now see guys, this one is a completely dedicated lecture to the SPPU M3 subject. So I'm just focusing that you all have to get familiar with all the concept, all important question for your SPPU question paper. Okay, so I hope you all have understood everything here in my today's lecture. So thank you everyone. Thank you for my today's lecture.